And the next part of our lesson is all about the use of the Arsoval meter movement in different kinds of applications. So one of which is in DC ammeter. So DC ammeter is a meter used in measuring the amount of current flowing through an element or a circuit by series connection. So take note, when we are using an ammeter, we're connecting it in a series connection. So what is the concept of an ideal ammeter? Always remember, an ideal ammeter has a resistance, a meter resistance of ideally 0, of course. But in reality, it has a very small resistance. So needle deflection is directly proportional to current. Take note of that. The deflection is directly proportional to current. So next. So we have ammeter errors. First, we have calibration error arises from the fact that meter phase is not accurately marked. But this is the one that we should remember. What is this? The ammeter and insertion error. So it's caused by the internal resistance of the ammeter. So take note, because of the ideally the internal resistance of an ammeter should be 0, but because of those small internal resistance, it introduces what we call the ammeter insertion error. And then the measures of reliability or the accuracy of the ammeter is simply the current with meter all over current without meter. So current with meter is the ammeter reading, while the current without meter is the actual current if we solve it via computation. And then we have what we call the percent loading error, which is 1 minus accuracy times 100%, or it's the same formula of the error that we have introduced in the previous part of the lesson. Next, we have the computation part, another computation part for the DC ammeter. We are about to introduce the DC ammeter shunt resistance. So this is a resistor connected in parallel with the meter to increase the measuring capability of the ammeter. So when we look at this part, we can see that there is a parallel resistor to our ammeter. Okay, so we call this parallel resistor the shunt resistance. And what is the purpose of that parallel resistance or resistor? It is connected in parallel to increase the measuring capability of the ammeter. Then we have the what we call the multiplying factor of the ammeter, which is equal to the IL all over IM. So IL is what we call the max current that can be measured by the meter, and IM is what we call the full scale current. So the full scale current is the current that flows on our meter, while IL or the max current is the current that flows into the ammeter. It is the maximum that can be measured by the ammeter. Then the multiplying factor of an ammeter is also equal to 1 plus the ratio of the resistance of the galvanometer coil all over the shunt resistance. So always remember this formula, the multiplying factor of ammeter. Then we have what we call the Ayrton shunt. So the Ayrton shunt is a shunt arrangement, which is also called universal shunt that prevents a meter movement from being used with no shunt. Okay, so it is very important for that uh, Jarson meter, DC ammeter, to have a shunt resistor so that uh, it will not be easily be destroyed by a large current. So here we have what we call the Ayrton shunt, wherein there is always a shunt resistance or the resistance in parallel with the meter. Next we have DC voltmeter. So it measures direct voltage across the element or circuit being measured. The concept of ideal voltmeter, if ammeter is having resistance of 0, ideal voltmeter has a resistance of ideally infinite. So we need a resistance of ideally infinite or a very high resistance. We can say it should be ideally open, while ammeter is ideally shorted. So we have DC voltmeter multiplier. Basic Jarson voltmeter movement can be converted to a DC voltmeter by connecting a multiplier to extend the voltage range of the meter. So in our ammeter, we have a shunt resistor, but this time in our voltmeter, we have a series resistance. So this series resistance serves the same purpose, just like the shunt resistance in an ammeter. It is to extend the voltage range of the meter. So again, we will see the formula of the multiplying factor of the voltmeter. So we have VL all over VM, or the max voltage all over the voltage drop across the meter, which is equal to 1 plus RS all over RM. So this time, we have the series resistance all over the internal resistance of the meter plus 1, which is what we call the multiplying factor of the voltmeter. Then we have the sensitivity of the meter movement. It is aid in determining the value of the multiplier and the reciprocal of the full-scale deflection current. Then we have tackled the error in terms of ammeter, but this time for the error in voltmeter. So the voltage across a component is less whenever the voltmeter is connected, and this is what we call the loading effect. So if the ammeter is connected in series, voltmeter is connected in parallel. Okay, so this error or this condition will result into an error called the loading error or the loading effect error. And then we have the ohmmeter. So the ohmmeter is an instrument designed around a basic meter movement that is capable of measuring resistance. So constructed with a basic Jarson meter movement in conjunction with a battery and a resistor. So take note of the components that we should remember when we're talking about an ohmmeter. So when we're talking about ohmmeter, what should we remember? We have a Jarson meter movement, and then with a battery, and of course a resistor. The basic components of an ohmmeter. Okay, and of course, if the error in ammeter is due to insertion error, for voltmeter is what we call the loading error. So the error in an ohmmeter is caused mainly by battery aging. So take note, battery aging is the main cause of ohmmeter error. Then we have the multimeter. It is the combination of three circuits in a single instrument. We have the VOM, or the volt, ohm, milliammeter. So it's a general purpose test instrument that has necessary circuitry to measure AC or DC voltage, direct current, or resistance. So typically, 50 microampere meter movement. So it can measure voltage, current, and of course resistance. Additional functions, it can be used in continuity check to know if the line is open or shorted. Then can also be used to check semiconductor diodes if they are faulty or not. Okay, so we're done with the DC meters, or the meters that are used to measure direct current variables. So we're going to the next part, which is the AC meters. So first we have AC voltmeter, half wave. It is a DC operated D'Arson voltmeter movement which is used to measure AC voltage. So how did it happen that it can measure AC voltage? By the process of half wave rectification. As we have discussed earlier, we can use the D'Arson voltmeter movement only if we have what we call the rectifier to measure AC. So without our rectifier, without rectification, the D'Arson voltmeter cannot be used to measure AC. So take note of that. So when we say half wave rectification, the component that we need to look is the diode, one diode for half wave rectification. Next we have full wave AC voltmeter. So here it is using a bridge configuration, full wave bridge rectifier. So the difference is it uses full wave bridge configuration. This is the component that makes it full wave. Next we have bridges, instruments for making comparison measurement. They are used to measure resistance, capacitance, and impedance. Operates in null indication principle, meaning indication is independent of the calibration. So we'll tackle null indication in the latter part. Let's proceed. So first of the bridges is what we call the Wheatstone bridge. So take note, we'll just highlight the important details here. So Wheatstone bridge is used to measure resistances. Take note, resistances with each branch containing two series elements, usually resistors. So this is the figure of the circuit of Wheatstone bridge. And then we have here a null detector, usually a galvanometer. So this is the galvanometer connected between the parallel branches to detect a condition of balance. And when we say balance, we say the bridge is balanced. It's noted here that to say that it's balanced, the reading in the galvanometer should be 0, meaning there will be no current that flows in the galvanometer. So when the bridge is unbalanced, the pointer in the galvanometer deflects, thus exhibits sensitivity. Okay, so as we have discussed earlier, sensitivity is the reciprocal of full scale deflection current. So here in Wheatstone bridge, you can find the unknown resistance given the network of resistances in bridge configuration. Bridge is what we call the Kelvin bridge. So take note of the differences when we use Kelvin bridge. It's the modified version of the Wheatstone bridge. Meaning, modified, it's better in measuring very low resistances. So take note of that, very low resistances. Unlike Wheatstone bridge, it is for resistance, but here we have Kelvin bridge for very low resistances. So it displays a high degree of accuracy because it can measure very low resistances, and the range is 1 ohm to 1 micro ohm. Okay, next. So application of Wheatstone bridge, it can be used in two types of tests: the Murray loop test and the Varley loop test. So we talk about Murray loop. So the simplest of loop tests and used to principally locate ground faults in sheeted cables. So to locate ground faults. Okay, when there is an open and you cannot detect where is it, so we can use the Murray loop test to know the exact location of the ground fault. Then we have the Varley loop test, a modification of Murray loop test, which is a special Wheatstone bridge configuration used to locate shorts. So it locates shorts between conductors or faults to ground in conductors. Next, so AC bridges that can measure impedances or can also measure capacitance, inductance, and impedance. So here we have the opposite angle bridge, what we call the Hay bridge. Hay bridge. Okay, so it measures the impedance of an inductive circuit. Take note of that. Hay bridge or the opposite angle bridge is used to measure the impedance of an inductive circuit. Next kind of bridge is what we call the Maxwell bridge. So for Maxwell, take note, inductance with capacitance standards. So also known as Maxwell-Wien bridge. Next we have Wien bridge. Measure the equivalent series components or the equivalent parallel components of the impedance. Of course, it is used in our Wien bridge oscillator, and we call this circuit the series and the parallel RC. We call this the lead lag circuit. Then we have the shearing bridge. It is used to measure capacitance. Take note, shearing is used to measure capacitance. Next, we have electronic instruments. So common and electronic measuring instruments like volt, ohm, milliometer. So we have already discussed this. Electronic voltmeter. So voltmeters that use active devices such as vacuum tubes, transistors, or op amps. Can be analog or digital. Depends upon the types of display. So if it uses deflection, we call that analog. If it uses deflection, while if it uses numerical type, it is digital electronic voltmeter. Then we have transistor voltmeter. So the name itself, transistor voltmeter, it uses transistor as active device. Then we have vector voltmeter, both magnitude and phase. Then we have vector impedance is impedances with both magnitude and phase. Other types of electronic instruments. So we're talking about oscilloscope. Oscilloscope. Ayan. So oscilloscope, device that contains cathode ray tube, of course, CRT, and it is used for representation of electrical signals, particularly analog signals. So different types or different parts of the oscilloscope are as follow: CRT, vertical amplifier, horizontal amplifier, sweep generator, trigger circuit, and associated power supplies. Then we have the reflectometer. So what is the use of reflectometer? Of course, it's used to measure reflected waves in the transmission lines. And when we're talking about OTDR, or the optical time domain reflectometer, so it measures the existence. It determines the existence and location of breaks in fiber, losses and splices and connectors. Then we have signal generators. The name itself, a signal generator, is a generator of different kinds of signals. Can be sine waves, square waves, triangular waves, and pulse train, as well as amplitude of the output signal. Then we have sine wave generator, the same. It's just mainly for sine wave. An audio frequency generator, a generator that can produce frequencies in the audible frequency range. Then we have radio frequency generator, self-explanatory. Then we have the pulse and square wave generator again. It generates pulse and square wave. Function generator, so it provides a variety of output waveforms over a wide range of frequencies. Then we have distortion analyzer. Of course, measures the signal distortion. Wave analyzer. So tuned to the frequency of one signal while rejecting all other signals components. So that's a frequency selective voltmeter. So wave analyzer is a tunable voltmeter used to measure the various frequency components of a signal. Then we have spectrum analyzer. So if we have oscilloscope that can display analog signals, spectrum analyzer is used to present graphically, usually on a cathode ray tube, the energy distribution of a signal as a function of frequency. Take note, frequency domain. So oscilloscope is time domain, spectrum analyzer is frequency domain. Then we have Fourier analyzer. So based from the calculation of discrete Fourier transform using an algorithm called the fast Fourier transform. Siyempre, social na siya. It provides high degree of accuracy, stability, and repeatability in spectrum. Then we have the Geiger counter. Goku. Vegeta. An instrumentation device that detects and measures ionizing radiation such as alpha, beta, and gamma particle radioactivity. It measures ionizing radiation. So in reality, the Geiger counter looks like this. It's not like that. Okay. And that's it for our lesson in instrumentation. So the next part will be the examination. Okay, so thank you for listening, and the next part will be our questions.